Thank you so much for the very kind introduction, Ambika, and thank you for inviting me to the LGP program. Welcome to all of you. Where should I start? So I am a confused scientist, and that's a good and a bad thing. It's a good thing because that means I can work on anything I want because I'm confused and nobody would know. It's a bad thing because I'm confused and so I don't know what I'm going to work on next. And I hope that over the next hour and a half or so you will see some threads associated with some of the things that I've had the good fortune of working on with students slightly older than you, on problems which you think are not problems at all. So a very famous scientist, Albert St. George, said, science is the ability to think what nobody has thought by seeing what everybody has seen. Okay, so, you know, everybody has seen many, many things in one's life. If you're young, you've seen a little less just because you're young. I'm older, so I've seen a little more. But if you think slightly differently, then perhaps you may be able to discover something new that other people haven't discovered yet. And I want to tell you about how, as a scientist, I think about what is in front of you, what is in front of us, but think slightly differently, and as Ambika was saying, think slightly more mathematically than perhaps might be typically seen. And I want to focus on questions which are at the boundary between not just within science, between boundaries associated with what is physics, what is chemistry, what is biology, and what is mathematics, but also between science and art, break that boundary, and between science and art and technology, and break that boundary as well. People think of science and engineering as somewhat different. They don't have to be. People think of science and art as somewhat different. They don't have to be. In both science and art, you have a creative aspect. I'm sorry, is there an echo that is bothering people? Maybe if the AV can help reduce, or if you want me to move this down. So I want to show you, using examples, that these boundaries are artificial. Today, you may work on a problem from a scientific perspective, and tomorrow you may decide to work on it from an artistic perspective. Creativity is important in both aspects. Today, you might decide to be a scientist because you're interested in understanding the world as it is. Tomorrow, you want to be an engineer, and you want to discover or create a world that never was. And so the differences between science and engineering, the differences between science and art are somewhat artificial. People you think of as great scientists may have done something remarkable in one aspect of science, but they also may be fantastic artists, artists who are great musicians, painters, and so on and so forth. But one thing somehow is more important in their overall oeuvre, in terms of their work that they've done. Okay? So I want to start by maybe just showing you a title and asking you a question. So I gave, when Ambika asked me what do I want to talk about, I gave a title of Unfolding Complexity, Maps and Shapes from Folds and Cuts. And so maybe my first question to you, and I hope this is interactive, okay? So is everybody over here, I'm sure, knows the word complexity. How many of you know the roots of the word complexity? Anybody willing to wager? Venture a guess? Anyone? Don't be shy. What is the origin of the word complexity, etymologically? What are the roots? Okay. So, since nobody's volunteering, I will tell you. So, complexity comes from complicare in Latin. So, com is together, plicare is to fold. Okay. So, complexity, which you think of as, oh, it's associated with complicated things, but in fact, it's associated with something which we do all the time. We fold our clothes and we unfold our clothes. You fold and unfold paper. In fact, your brains are folded, your lungs are folded, your intestines are folded, my hands are folded right now. So complexity is essentially a very beautiful word because it describes how things are folded together, and what you're trying to do when you're trying to unravel complexity is to unfold it. Simplicity comes from simplicare, single fold, one fold. So when you're trying to simplify a complicated thing, what you're trying to do is to unfold it. And what I want to do is to tell you about complexity in the context of maps and shapes, but I want to do that by basically first introducing you to a subject which you might think has nothing to do with science at all. I want to start with archaeology. Okay? And archaeology, which is associated with studying artifacts that people built from the past, if you're thinking about what a historian might want to do when he goes into an ancient part of the world by digging deeper and deeper. And so archaeologists define different eras of material culture in terms of the human mastery of and manipulation of matter. So you probably have heard of the Stone Ages or the Lithic Ages in your school. So the Lithic Ages are associated with the ability to essentially manipulate matter, such as stones, to create tools. So humans at some point were thought of as unique because they had the ability to essentially create tools, but in fact we now know that animals can also create tools. So what kinds of tools? Tools associated with stone axes or arrowheads or primitive knives. So you had the Lithic or the Stone Ages. Then you had the Bronze Ages, where what did you do? So instead of breaking material, you essentially heated material, and you heated material, the material essentially melted if it was a metal, and then when you melted it, you could essentially mold it into something, and then you created other kinds of even more sophisticated tools. So you went from the Stone Ages to the Metal Ages. First the Bronze Age, then the Iron Age, and so on. And so in the first case, you're playing with brittle materials which are easy to break, and when they're easy to break, you can essentially make sharp things. You can make sharp things, you can essentially manipulate nature around you, okay? But you can also do it by changing temperature. You change temperature, if you increase the temperature, ice becomes water, water will become water vapor, or a metal will essentially become a liquid, and then you can pour it into complicated shapes, and then you allow it to essentially settle down, cool, and you can get complicated shapes. Again, you can build complicated tools. So the mastery of materials was very, very important in our own history, and in fact, it's also important in the context of animal behavior. And this continued until the dawn of the Industrial Revolution a couple of hundred years ago. And as the Industrial Revolution essentially developed, we were able to enhance our ability to essentially concentrate power and concentrate forces and do all kinds of remarkable things, which allow us to live the way we do today. But if you look carefully, and if you look at archaeology very carefully, you also see, in fact, that there was a parallel culture, and the parallel culture was associated with the shaping of very soft materials, materials such as clay. How do you manipulate clay? You add water. When you add water, the clay softens. When clay softens, how many of you have practiced pottery? At some level, a lot of you, right? So what do? The most important thing is to essentially use water to soften clay, and then you can use that softened clay to mold it into any shape you want. And then you allow it to dry, and you've got now a new shape, and that shape essentially might have function. So people started manipulating with not hard, brittle materials or using the change of phases. They started basically playing with soft materials, like clay, or like skin, like cloth, like fiber, and like paper. So they started manipulating all these materials, which are very soft, and instead of using large forces and high amounts of energy, they were using, so not brawn, but they were using their brains. They were starting to use, now I can essentially manipulate all these soft materials like skin, like cloth, and make very, very sophisticated materials like the things that you and I are wearing, cloth, or the things that I used to write on, maybe you still write on, maybe you write on tablets, but I see at least a few people have still pieces of paper, okay? So you can essentially start seeing a transition from, instead of working with hard materials and brittle materials with very high amounts of power, you work with soft materials, and you work with now the structure. So you work with geometry. Geometry comes from, again, etymologically, geometry is measuring the earth. Geo is the earth, and metry is to measure. So geometry is essentially now playing with structure, playing with understanding how if I take individual filaments and then I can weave them together and I can create something complicated like a cloth, and the cloth is complicated because not only is it flat, it can drape some very complicated object like you or me, okay? So instead of playing just with power and force, you started playing with structure. You started playing with geometry and topology. What is topology? Topology is different from geometry in that if geometry thinks about characterizing lengths and angles, topology characterizes things which are essentially connected or disconnected. For example, a donut is different from a sphere because a donut has a hole in it. Okay? So there was a transition from thinking about strong large forces and high amounts of energy to thinking about cleverly manipulating structure. Why did we want to do that? Because we want to have function. What kinds of functions? Everything from textiles to complicated materials, which nowadays we think of as soft antennas and whatnot. Okay, so what I wanted to tell you in science, and so who were the first people to do this? The first people to do this were not scientists, they were not mathematicians, they were not engineers, they were artists. They were artists and they were artisans. And what I want to tell you about in the next hour or so is stories associated with how artists were so far ahead in terms of their imagination have inspired scientists like me and perhaps scientists like you in the future to essentially think about combining the arts with the sciences. Not think of them, this is art and this is science and that is engineering, but in fact these boundaries are continuously evolving and should continuously evolve because they're associated with completely artificial ways of thinking. What is art today may become science tomorrow. What is science today can inspire art tomorrow. And similarly with science and engineering. Sometimes people think, oh, science comes first and engineering comes later. That's not true. Often engineering essentially allows you to create tools and build ways of measuring things which were not possible. And so engineering can enable science. So we shouldn't think of these different fields as having hierarchies or actually even being different because they're all intertwined with each other. And I hope you'll see this through the example that I want to tell you about. So forgive me for this long introduction, but I think it's useful to put this in perspective, particularly because you are a lot younger than me, even younger than our children, younger than my children. Okay, and I want to start by telling you about a way to unravel complexity by using maps. So what is a map? So a map is a way to describe relationships. Would everybody agree? Right? So if I give you a map of Delhi or Sonipat, you will tell me how do you draw it? Well, you will draw it not on the scale of the entire city or the country. You will draw it on a small scale. So what is the most important thing about a map? Location of a place relative to other locations. You cannot have absolute location. I don't care. I care about, and you probably don't care, to know where Sonipat is in the absolute coordinates unless I tell you what are absolute coordinates. Well, absolute compared to what? Compared to the center of the sun? Not very useful. Compared to Delhi? Very useful. Right? So maps depict relationships. And relationships, therefore, because of the nature of maps, you don't have to draw something on the scale of the planet or even on the scale of Delhi. You can draw a map on a much smaller scale. But you still want to preserve relationships, which means you want to preserve relative lengths, distances, and relative angles, orientation. If I ask you to go from here to any other part of the university, or if I ask you to go from one part of the country to another, you need to know distances, but you also need to know orientations. Okay? So you can ask a question, is it possible to always construct a map of a complicated surface? For example, the surface of our Earth. How many of you ate an orange in the last 24 hours? How many of you ate an orange in the last month? A lot of you, okay. And everybody peeled the orange. When you peel the orange, how many of you realize that you cannot peel the orange and keep the surface of the orange peel flat? Once you peel it, okay, so you have to make a cut, you have to open it up, can you essentially flatten that peel? No, okay. So this is something that all of you have experienced. But in fact, it was not until the middle of the 19th century, due to a very famous mathematician, actually three of them, the most famous you probably have heard of, called Gauss, okay? And two others who more or less simultaneously did this, Bolyai, a Hungarian mathematician, and Lobachevsky, a Russian mathematician, proved mathematically, and I'm not going to go through the proof, but I'm going to tell you, proved that there are certain things that you can do and certain things you cannot do when you're trying to represent relative orientations and relative distances. In particular, they proved that you cannot essentially flatten a sphere. Impossible. Unless you stretch some part or shrink some part. But when you stretch or shrink, that means you're changing relative distances. So that means that it is impossible, mathematically impossible, to essentially take a curved object like the surface of a sphere or an orange and flatten it. Impossible. Question. They are all incorrect, not technically. They are all incorrect. Immediately, okay? And I invite you from now on, for the rest of the course, every day to try and play with some part of the world, okay? Look at Google Earth, for example, and use Google Earth to see something about how relative distances are shown on the surface of the Earth, because Google Earth will actually have a spherical representation. And then go to a map which is associated with different projections. So each projection Each approximation has the name of somebody who essentially created some version of how you flattened your orange. Some of you peel an orange, for example, by having a spiral. Some of you peel an orange by having cuts along longitudes, and so on and so forth. So Gauss and Lobachevsky and Bolyai showed you can't do it in general. So what do? You can either just fold your hands and say, I quit, or you can say, no, I don't care. I'm going to make an approximation. I'm going to make levels of approximation, and these levels of approximation are what artists are very good at. Artists don't want to depict the world exactly, because if you want to depict the world exactly, you basically just create another copy of the world. What an artist wants to do, what an artisan wants to do, is to essentially create an approximation, and that approximation evokes in all of you an emotion that the artist wants to essentially use to tell you about something else. But scientists do the same thing. Scientists also don't want to create a world which is exact. What scientists want to do is to create an approximation of the world which allows you to understand relationships between different parts of the world. And so I'm going to use maps to essentially do this for you, with you. I'm going to use maps to essentially characterize how you can approximate any shape by having folds or cuts. Okay? And I'm going to use origami and kirigami. How many of you have had some experience with origami? Everybody, which is great. How many of you know etymologically, and I'll come back to this, we'll forget about etymology now. How many of you had experience with kirigami? Okay. Can people who have not seen kirigami, people who have experience with kirigami, just shout out what is the difference between kirigami and origami? Anyone? Thank you. So kirigami is the idea that instead of having folds, you essentially have cuts, but you can't just cut randomly, because if I cut randomly, I'll take the piece of paper and make it into as many cuts, as many pieces as there are large cuts. Instead, you want to have cuts which allow the paper to be articulated so that you can essentially rotate one part of the paper relative to the other. And you use that so that you can essentially, again, do something which you can't do with a piece of paper, which is to essentially, for example, drape my head, which is partly spherical, or my shoulder, which is even more complicated. Sorry, my neck or my shoulder, which is even more complicated. Okay? So artists have done this, and the question is, what can science tell us about that? What can mathematics tell us about that? And that's what I want to do. Okay? So, why did it go off? Okay, so, so origami comes from the Japanese, actually initially Chinese. You can see the Chinese characters if you know Chinese over here. From oru, which is fold, and kami, which is paper, and kirigami comes from cutting paper. Okay, and here are some samples, examples of origami. A very ancient one, which everybody essentially probably has experience with, is essentially taking a sheet of paper and constructing a boat or a dragon. I mean, it's very, very interesting to create complicated shapes, and the question is, how do you do this? And I'll come back to that. Or create a range of shapes, like a flower vase, or a pill, or a part of a sphere, or even a map. Okay? This is a map of essentially a subway system in Tokyo. And it's a map that you can fold and put into your pocket. And I'll come back to this because it's a question of how do you fold and how do you unfold a map. That's on the scale of humans, something that you can hold in your hand. This is on the scale of a micron, so a millionth of a meter, so you cannot even see. You have to use an electron microscope to see this. And you can see, again, people have been using these origami-like structures to create folds. And I won't get into the details, but these folds allow you to essentially change the electronic properties. And by allowing you to change the electronic properties, you can create something like a graphene sheet into a semiconductor. Okay, a graphene sheet is one layer thick sheet of carbon. What can you do with kirigami? So you can again create complicated patterns. For example, this is a flat sheet, and you pull on it, it opens up, and it can essentially create something which you can use to drape around your shoulder or your neck. And again, it's not limited to the large scale. This is on the very small scale, and I'm sorry that I forgot to put the scale bar. This is of the order of a micron. Okay? So what you see over here is that what matters, hold on one second, what matters is that the thickness of the sheet is much, much less than the other two dimensions. And once the thickness is much less than the other two dimensions, it doesn't matter what the absolute scale is. So again, origami and kirigami can be thought of as ways to essentially create maps. And it doesn't matter on what scale you do it, because what matters is that you do it in such a way so that you preserve relative lengths and relative angles. Question?
When we're kids, a lot of us have an experience with like taking an origami sheet, folding it, and like cutting it to make a snowflake and all, right? So will that count as kirigami?
Will what?
Like taking a origami sheet, folding it, cutting
Sorry,
it.
what was the question?
Like, would cutting an origami a lot of us have experience as like taking an origami sheet, folding it and cutting it to a snowflake or something of the sort. Will that count as kirigami? Also, I saw somewhere
No, if you're folding it, it's not origami.
Okay.
If it's not kirigami, it's origami.
Yeah.
Okay?
Also, I saw somewhere that these people were doing a challenge that they were taking an A4 size page and they were essentially cutting it so that they could walk to it. So
that they could what?
Walk to it, like they were cutting in a way so that it became like greater than it was and they could walk to it.
I didn't understand. Walk through it? What do you mean walk through it? Oh, yeah, sure.
Yeah.
But what is the question?
Like technically they had to fold it first, but would that still count as kirigami?
That would, if you're cutting it, it counts as kirigami. Sure.
Yeah.
Okay. Okay. So, very important thing, which I think all of you have experience with, and there is a mathematical way of defining that, is you take a sheet of paper, it's impossible to stretch it, very easy to bend it. Okay? I can bend it in one direction, I can bend it in the other direction. I cannot bend it in both directions without creating creases. So I'll try to bend it in one direction, and now I try to bend it in the other direction. You see what happens. I start creating complicated structures. And so, very simple question. This is a crumpled sheet of paper. Most of my calculations throughout my life have ended up like this, which I can put in the dustbin. Okay? So that's a failure, you would think. But it's in fact a wonderful failure, and I can tell you right now that we do not understand at a mathematical level, at a physical level, at any level, we do not understand the patterns associated with a crumpled sheet of paper. And so, you know, when as a budding scientist, as a budding engineer, you want to think about, oh, I would like to study black holes, I would like to study quantum mechanics, things which are very large, things which are very small, but there are plenty of problems on the scale that you and I and everybody else can experience which are just too hard even now. We do not have an understanding of a crumpled sheet of paper. What do I mean by that? I mean that I cannot describe, and nobody that I know, in fact I don't think scientifically we know, a way to describe the intricate patterns of crumples that you see in a sheet of paper. And so why am I giving you this example? I'm giving you this example for two reasons. I'm giving you this example because it's for, first of all, it's inspiration. I think it's inspirational that, oh, I can do an experiment, I can measure. What do I want to measure? I want to measure the relative angles of the creases, the relative lengths of the creases, and then if I reproducibly crumple it, can I say something about how likely it is that I'll get the same kind of pattern? Do not know how to explain that. So this is kind of crazy, right? You would think that we understand so many things, and yet we don't. Question? Understanding the statistics of the angles and the lengths of the creases that you essentially have when I have a crumpled sheet of paper as a function of the volume in which I've essentially enclosed the sheet.
I have a problem with saying how do we understand crumpling of paper mathematically? How will you describe crumpling paper mathematically?
Yeah, as I said, I take a sheet of paper and I put it in a volume and I reduce the volume, and now subject to the fact that the lengths and the angles have to remain essentially the same, what kinds of structures will I get? And I can essentially, maybe offline, tell you about the energetics and the statistical mechanics of how you think about that. But perhaps that's better that we leave it outside. Does that at least give you a sense of what? Yeah.
So my question is that at the starting you told we are trying to figure out how origami and kirigami in the aspect of science and maths. So have there been examples in the past where we've looked at scientific and mathematical examples artistically?
Yes. Ask me that question at the end and I'll come to it, because I want to first tell you about how we can think about art and science mathematically, and at the end, if I understood your question, you want to know whether I can think about science from an artistic point of view, right? Yeah. So will you ask me that question at the end? Again, if I forget to answer it. Okay. All right. So what do I want to do? So I want to basically ask the question. So since artists use origami and kirigami to control shape, I want to ask the same question now from a scientific point of view. How do I control shape? One way to control shape is to play with the material. Okay, I can use wood, I can use clay, I can use metal, I can chip on the wood, I can nap or break the rock, I can heat the metal so that it melts, I can use that. But that's sort of use lots of forces, lots of energy. And I don't want to do that. I want to essentially be clever about it. And one way to be clever about it without using a lot of energy is to play with structure, which means understanding who's connected to whom, where are they connected, how are they connected, which means therefore I think about folds, I think about cuts and so on. And that in mathematics is associated with playing with geometry and topology. As I said, geometry is associated with understanding lengths and angles. You can be more sophisticated about it, but for now I'll leave it at that. And topology is associated with understanding connections. And there's a whole field, in fact, many fields of science where people have started working with playing with geometry and topology rather than material to create, for example, perfect mirrors or mirrors which will essentially do strange things to an image of the object or materials which can essentially conduct electricity without having almost any resistance or in a mechanical context, which I'll tell you about, do something crazy. Like imagine, I told you that I can take a sheet of paper and I can't drape my head, or I can take an orange and I can't flatten it, but I can do it approximately. And how well can you do it approximately is an interesting question. Okay? And the idea and the notion of these fields is associated with creating what are called metamaterials. Not just materials, but metamaterials. Metamaterials are materials which now have a sense of structure on them, and therefore they have properties which are very unusual. Perfect mirrors, perfect conductors, perfect drapability, and so on. Okay? Experience tells us, and mathematically it's a fact, which I won't have a chance to really get into, is that any sheet which is thin, which means, what is a thin sheet? One dimension is small compared to the other two dimensions, is very, very easy to flex, to bend, and extremely hard to stretch. And that's independent of the material. If you've had one of these fancy new phones, which I have not seen, I've only heard about, which are flexible. Well, they're made of glass. Okay, they have a thin sheet of glass, and the glass is so thin that I can bend it. You try to bend a thicker sheet of glass, it will break. So as soon as you have one dimension which is small compared to the others, immediately you can fold, and you can't stretch. And I want to emphasize, it's got nothing to do with the material. It's got to do with the geometry. Okay, and so because it's capable of flexing easily, well, you can flex it very strongly. You can flex it strongly to create a crease. I just created a crease. And what is origami? Well, origami is the ability to find patterns of creases so that I give you a flat sheet. Here is the pattern of creases, and if I fold in the right order, the right place, so in time there is an order, and in space there is a pattern. I cannot fold here first and there later. I have to essentially give you not just this pattern, I have to give you a particular order. And once I do that, then I can convert a sheet into a crane, a sheet into a dragon, a sheet into a boat, and whatnot. And what is the basic building block? The basic building block is just this very, very simple object. This extremely simple object where I take a flat sheet and I folded it. When I fold it, you see that I've created one vertex, one point, from which there emanates four edges, four creases, and these four creases always will have three creases of one sign and one crease of the opposite sign. Always. Okay? You can play with this through experience. You can also prove this mathematically, and I will not talk about the latter, I will simply show you. Okay? All right, and so with this, from this, if I have a whole bunch of them, then I have the ability to create a complex origami pattern like a crane. And so the building block is a four-creased vertex. It's a four-creased vertex, means four lines come together. If I play with cuts, in fact, turns out, and I forgot to bring a model, and I couldn't really create one this morning, with cuts instead of folds, you can also have something which is now a four-coordinated object, but it's a four-edged hinge. So this is a set of squares, and you can see the squares are connected as I've shown you over here. And I invite you to think, I said, I'm sorry I didn't bring a demonstration of this. If I essentially start rotating each one of these squares, all the other squares will rotate, and the whole thing will collapse and close. Do people see that? Do people recognize that? Okay, if I have one of these over here, I can rotate the squares and it will collapse, and if I open them, all the squares will open, and then I get a volume. I get a lot of empty space, and the basic building block is a 4-coordinated hinge. At every one of these hinges, you will see 4 edges coming together. Okay? And so, what is the question? The question is, if I'm not allowed to stretch the piece of paper or change any angles, but I allow you to introduce these creases or folds, and I allow you to introduce these cuts, which mathematically means something very technical. It says that no lengths are allowed to change, no angles are allowed to change, except at a small number of points, and those points are the hinges and the vertices. Okay? These points, these vertices over here. Except at those points, I'm not allowed to do anything to the sheet of paper. What can I essentially create? And artists have shown us that we can create almost anything. We can create a dragon, we can create an approximation to a face. You can do this on the small scale, you can do this on the large scale. And so the mathematics question, the science question, the physics question is, can I essentially create mathematically a framework which mimics what artists have known for 1,000 years? Is the question clear? Okay? So in answer to your question, this is the first part of it. So given an artistic expression, can I understand the scientific basis for it? And you might think, oh, this is terrible because I'm taking away the beauty from the art, but in fact, I would say exactly the opposite. You can appreciate the art just like an artist can, but if you know the science, you can appreciate it even more and more deeply. Okay? Oh, yeah, this is the energy density, which is how much does it cost to essentially deform a sheet of paper. And I'll just tell you, but I won't be able to get into any details. I'll tell you that it's much easier to bend a sheet of paper and much harder to stretch a sheet of paper. And that's because stretching a sheet of paper is proportional, the energy is proportional to the thickness, while bending is proportional to the cube of the thickness. So if the thickness goes to 0, which one of these goes to 0 faster? The cube. And because the cube goes to 0 faster, it's much, much easier to bend a sheet of paper or a sheet of glass than to stretch it. That's what I've written over there. But again, that's a detail which is not important. Hold on, okay? All right, so instead of thinking about a continuous approach, you can think about a discrete approach. So rather than thinking about understanding how to do everything smoothly, I can say, I want to discretize everything. And in fact, it's not a surprise that it makes things easier and better. All of us now live in the digital age, and the digital age is essentially fundamentally associated with saying, instead of thinking about things continuously, I think about things discretely. Be wise, discretize, somebody very famously said, and if you discretize, you can make a lot of progress. Okay? And so the discrete way is, instead of thinking about topology and geometry and material continuously, I ask, how can I change the number of folds? And every time I say fold, you can replace it by cut. How can I change the number of folds or cuts? How can I change the coordination? How many of them come together and where they come together? How can I change the size of the folds or cuts? How long they are, where they are? How can I change the orientation of the cuts? What is the angle of the cuts? And how can I change their location? By changing these 1, 2, 3, 4, 5 in space and in time, potentially, can I do anything? That's the mathematical question. You had a question.
It's proven that we can only fold a page like 7 times, right?
That depends on what the sheet of paper is made of.
If you have an A4 size normal page, right, we can only fold it 7 times.
What's the question?
So if you were to do it with Kirigami, do you think we will be able to fold it more times?
Yeah, because with Kirigami, the sheet has got a cut over there, and so I can just keep wrapping it on itself, and then eventually it will tear and break at the hinge.
Yeah. So what is the most we can do it without it tearing or breaking? What is the most we can fold it using Kirigami so that it doesn't tear or break?
It depends a lot now on the material properties, and I want to think about the geometry, I don't want to think about the material.
Like the normal sheet you have there, normal A4 size.
I don't know, we will try it experimentally.
Okay.
Yeah. Okay, so the question is, instead of solving what we think of as the forward problem, you or I give you the creases and I give you how to essentially fold them. You come up with a crane, but who discovered that? An artist playing many, many times with many, many different versions of the creases and the folds or the cuts. They played and played and played, and empirically they found, if I do this and I give you the instructions, you can reproduce what I did. All right? That's part of the question. A much more interesting question scientifically, mathematically, is the inverse problem. If I want to essentially create a particular shape, how should I prescribe the number, the coordination, the size, the orientation and location of the cuts or the folds in order for me to be able to get there? Much harder problem. But artists have essentially shown that they can do it. What they did it, or how they did it was by trial and error. And I want to ask, and I want to show you, at least I want to show you in outline, how a scientist can think about this and show, oh, I have a shortcut. But in order to understand that, I have to understand the basic mathematical principles and the scientific principles and the computational principles. So I want to give you a sense of that over the next 20 minutes or so. And so I'm going to now speed up because I've shown you what the question is, which is the hardest thing. In science, the hardest thing is not answering the question. The hardest thing is asking the right question. Okay? It's always the case. We think when we teach, oh, I want to teach you how to solve a quadratic equation. I want to teach you how to solve a cubic equation. I want to teach you how to solve a differential equation. That's eminently doable. And in the age of AI, in fact, a computer can tell you. But what a computer can't tell you is how to ask a good question. And what I want to show you is that once you ask an interesting question in a good way, in the right way, the answer just follows very, very easily. And I want to do that because we were inspired by artists who essentially showed us the way. Okay? Okay, so where to start? So I told you I want to define a word, isometry. Isometry means you preserve all lengths and you preserve all angles. In the case of origami, it's piecewise flat, which means locally. This object that I showed you is flat. It's made of flat objects, another flat object, another flat object. They're coming together along creases. You can only rotate objects, right? You can rotate only, all these flat planes are being rotated. They're rotating in 3 dimensions. It's very complicated, but it's just a rotation. Because I'm rotating in this direction, I'm rotating in that direction, I'm rotating inwards and outwards. So in Kirigami, first we can think about rotating in the plane. Eventually we'll think about rotating out of the plane. And now I can prescribe either the topology or the geometry, which means what? If I prescribe the topology, which means connectedness, I say that the creases always come together in 4-fold vertices. If I prescribe the geometry, I prescribe now the faces themselves, and then I allow the number of creases to be arbitrary. Then I don't prescribe it. Today, I will only focus on prescribing the topology. It's a little easier to explain, but you can essentially solve the same problem by prescribing the geometry and varying the topology, varying the connectedness. Okay? And I'm going to show you a set of patterns, one of which I created a few minutes just before you came in, which is this object over here. Okay? This is a very, very well-known origami pattern, which I'm sure everybody over here who's played with origami knows. It was first discovered or invented, depending on your perspective, by a Japanese engineer called Koryo Miura. So it's called the Miura Ori, Ori for fold. And he then patented it. But what he didn't realize, which we did a few years ago, was that that pattern, in fact, appears naturally in leaves. It appears naturally in your intestines, very naturally. You can see that over here. It appears when you essentially have a piece of jello or jelly, which dries, and you can essentially solve the problem mathematically. So there's a good reason that, in fact, Koryo Miura essentially invented this, but what he didn't realize is that nature has essentially come to this problem again and again. Why am I showing you this? Because you can see, I think everybody over here who's close by can see that at every one of these vertices, you have 4 creases which come together and you just repeat it. And so what's the question? Well, this is something that everybody over here can fold. I mean, it may take you 5 minutes. It takes me a little less because I've done it a few times. Question is, this, of course, is flat when I open it up. It's also flat when I fully fold it. So it's flat, what's called flat foldable. And now the question is, how do I essentially design the origami so that I can move these creases around and move them in such a way and change their orientation, change their size, so that I can take this and make an approximation for a hat, or for a neck brace, or for a shoulder brace. Is the question clear? Okay? All right? And in particular, can I do something crazy? Can I take this Miura Ori? And this is, as I said, the result of most of my calculations. That's hard to understand and not very useful. Can I do something crazy so that I can, for example, drape the Miura Ori around a donut, an object with a hole? And this is a very, very hard question. It's also a very old question. It was first asked by, in fact, a very famous mathematician from the 19th century, German mathematician who was a student of Gauss called Riemann. And in the 1950s, how many of you have heard of or seen the movie A Beautiful Mind? A lot of people. So you remember the story of John Nash, who was very famous for his work that he did when he was essentially a graduate student, which led to a Nobel Prize in economics. But his most famous work, if you ask people who understand his entire work, is not what he did in economics, which was literally a 20-page thesis. It was his work in essentially trying to understand what Riemann did in asking the question of, is it possible to take a flat sheet and drape something so complicated as a torus or a sphere? It's called the Nash isometry or convex integration theory, which was essentially first formalized by Nash and then really lifted to a whole new scale by a Russian mathematician called Gromov. The reason I'm telling you all these names is also because science is wonderfully international. You know, people who do something over here influence people who do something in a different time, in a different space, at some other location, then it's picked up by somebody else in some other location. So it's wonderful. It's wonderfully international. And you know, I'm saying this because that's one of the things. You can travel with your body, but you can also travel with your mind. And there's nothing so spectacular as traveling with your mind across space and across time when you essentially learn all these wonderful things. So this problem was given a sense and an understanding from the point of view of Nash. And what Nash did was something very beautiful. I'll give you an inclination of that. What Nash said is, instead of thinking about smooth deformations, I'm going to think about non-smooth deformations, which means deformations. How many of you have had some exposure to calculus? Few people over here. Okay, so the notion of smoothness is associated with how easily or how strongly or how weakly does the slope change, or the slope of the slope, or the slope of the slope of the slope, and so on and so forth. Okay, so what Nash realized is I can relax the conditions on how many slope-like objects exist, and I can solve the problem. And that was the idea of Nash. It's a very technical field, but the idea is very simple. It's I relax the condition on smoothness, and when I relax the condition on smoothness, I can do things which I would not be able to do otherwise. Okay? So, what's the question? I start with this hydrogen atom. It has exactly 1 degree of freedom, so I want to explain what that means. 1 degree of freedom is all the faces move simultaneously when I pull on them. Okay? Make sense to everybody? All of them move simultaneously. And in fact, that's true not only of that one object, it's true for this object as well. All the faces move simultaneously. So this object has just 1 degree of freedom. And you can count this in a very simple way. I won't get into this. And that 1 degree of freedom allows you to take a map and fold it and unfold it. Okay? So what's the question? That's the hydrogen atom. That's essentially the same thing repeated many times. And the question is, this is completely periodic. It's developable, which means I can essentially flatten it out and fold it. It is flat foldable, so I can collapse it. It's what is rigid foldable, which means it has just 1 degree of freedom. I can open and close it in one motion. And it's got a peculiar property. Most materials, it's worth pointing out, most materials, when I pull in one direction, what happens in the other directions? Not someone else. What happens when I pull? Yeah. If I pull on one direction, usually the other direction will contract. If I take a sheet of rubber or a bar of rubber and I pull it in one direction, the other 2 directions will contract. Right?
Yeah. Yeah.
You mean contract, I think.
Yeah, I meant that, yeah.
Okay. But with a sheet of paper like this, you see when I pull on it in one direction, what happens in the other direction? It expands, so it's very unusual. That's why it's called a metamaterial. It's a material which has unusual properties, not because it's made of paper. It's got unusual properties simply because it's folded. Okay? And in fact, my favorite example of a metamaterial, which I hope you'll remember forever, is a crumpled sheet of paper. Because if I take a crumpled sheet of paper and I pull on it, it's expanding in other directions. It's not contracting. So crumpling introduces these constraints associated with the edges, change essentially what happens, and give rise to these unusual properties. Okay? So that's what is called auxetic, or forget this technical definition, it's called the Poisson ratio, which means if I pull in one direction, what happens in the other 2 directions? So this is completely periodic. And what's the question? Given these creases, okay, can you design their geometry, which means can you design their size, how long they are, where you should put them, how you should orient them to achieve any shape? That's the question. That's the inverse problem. The forward problem was, I give you a sheet of paper, and I give you the patterns associated with creating a crane, and I give you the instructions, and you go home and create it. The interesting question that you can ask is, how in the world would you think about essentially replacing the artist with an algorithm? So that if I know where I want to go, I want to get to a crane, and I know where I started with a flat sheet of paper, how can I essentially do that? Okay? And at the same time, I want to keep it flat, because of course if I can tear it, I can do anything I want. I want to keep it flat, I don't want to tear it. I want it to be rigid foldable, so that in one motion I can do this. And by the way, I think everybody over here, all the students are too young to have played with paper maps, but somebody like me and a few older people have played with paper maps. And so something peculiar about paper maps is, how do you essentially fold paper maps? You always fold them perpendicular to each other. Okay? So if you fold them perpendicular to each other, each fold is independent of the other fold. Everybody agrees? And if each fold is independent of the other, if you have n potential folds, you have 2 to the n potential configurations, because for every fold you can have it this way or that way. Okay? So this is strange, because and that's why, for those of you who remember, that means the older people, when you essentially have to unfold a map, it's easy. But to fold a map is impossibly hard, because you get confused. And this is a tribute to human stupidity. Okay? Why do I say that? Because if the folds were not perpendicular to each other, if the folds were at an angle to each other, the whole map will open in one motion and close in one motion. I can't understand why we never thought of essentially having folds which are not perpendicular to each other. Actually, I know why. Because it's easier to manufacture folding conditions associated with perpendicular folds. It's much harder to do this. But nature has done this otherwise. That's why I showed you in the leaf, in the wing, in the gut, in so many places you have non-orthogonal folds, and non-orthogonal folds allow the entire system to be compacted simultaneously, which is very important if I want to think about function. Okay, so I want all these degrees, I want all these constraints to be preserved, and so I want to basically now ask, okay, so what are the constraints? The constraints are, so I will describe in words, and I'll show you some examples. The constraints are that each one of these faces associated with this object, each one of these faces associated with this object has 0 volume, right? Because it's flat. The object has 0 volume. The angles at any location, at any vertex, must add up to how much? How much? Sure, I'm going to have a vote. How many say 180? Good. How many say 360? Thank you. Okay? So all the angles, if sum the angles, they must add up to 360 degrees. All right? Does everybody understand that? Because I've just gone around a circle. Okay? But there's something else which is equally beautiful, which is everybody can see this red angle. Okay? This red angle is the difference between this angle and that angle. Would people agree? But it is also the difference between that angle and that angle. Do people agree? So write it out for yourself now that I've shown you this, and that gives you a second constraint. And the second constraint is not only is the sum of the angles going to be 2 pi or 360 degrees, but the sum of the opposite angles, alpha 2 plus alpha 4 and alpha 3 plus alpha 1, must also be equal because of what I just told you. And that means that that opposite angles add up to 180 degrees. Okay? And this is very cool. It's in fact known to origamists, but it only was proved mathematically 20 or 30 years, actually slightly more than that, 40 years ago or so. And so we need this condition to be satisfied at every fold, at every vertex. Okay? So now the inverse problem, the mathematics problem, is force these constraints. I want the sheets to be flat piecewise, so every part of the sheet must have 0 volume. At any vertex, the angles must add up to 2 pi. And furthermore, if I look at opposite angles at every vertex, they must add up to pi. These conditions must be satisfied. And now what am I going to do? I'm going to allow you to move the vertices around. I'm going to allow you to move the vertices around so that instead of getting something simple and periodic, I get something which can map onto my head, my neck, my shoulder, my arm, and whatnot. Question clear? Okay. That's not clear. So what can somebody who was not clear, can you tell me what was not clear? If you like. Otherwise you can ask me later. Okay, I will wait. All right, so now I have to question.
So if the sum of all the angles is 360, that means pi would be 180, right?
Correct.
So if it's not necessary that angle alpha A and alpha 1 and alpha 3 are equal to 180.
No, not at all. Not at all. The only condition is that these 4 angles must sum up to 2 pi and the alternate angles must sum up to pi. But because I have 4 unknowns and only 3 equations, I have many different solutions. And that's the key. Because I have many different solutions which can satisfy that, that means I can vary individually the angles as long as when I sum them up, I get 2 pi, and when I sum up the opposite angles, I get pi. So that means I have a degree of freedom. Do you understand? Which means that because I have more unknowns than equations, I have 3 equations, but I have 4 unknowns, which means I can play. But that's important because without that, the artist would not have been able to do anything. Does that answer your question?
So that brings about more, variety in.
Exactly. That gives you enormous variety.
Yeah.
Okay? And that's what artists have been using all the time. They've been using this idea of degenerate solutions, which means many more solutions which satisfy the constraints, and therefore they can do origami. Because if they weren't able to, and artists realized that 1,000 years ago, they didn't need mathematics. And mathematics is sort of gradually plodding along and saying, now I understand why the artists had the freedom that they do. Art is fundamentally about freedom. Science is about the lack of freedom, constraints, because as I introduce laws, Newton's laws, Schrodinger's equation, Einstein's equations, Maxwell's equations, those are constraints which say that the world must satisfy these laws. But in fact, these laws are associated with different hierarchies. On the large scale, you have one set of laws, on the smaller scale, you have another set, and they have to be smoothly able to interpolate when you go from one level to the other. So there is a tension. And I'm sorry I'm being a little metaphysical and philosophical, but it's important because art is all about freedom, science is about constraint. If you didn't have constraints, I wouldn't be able to predict anything. Those constraints we call laws.
Yeah.
Okay, so mathematically, you can say that these are some constraints, but artists recognize that you have freedom too. And now as a scientist, I say, what is that freedom going to tell me about? Ask me what I want to do. The scientist says, how should I vary that extra degree of freedom in order for me to do anything with origami? Which is mimicking the artist. How as a scientist should I do this, or a mathematician? Okay, okay. So I will not get into the technicalities, and I'm reaching the end of the hour, so I'm going to show you some examples. First, I want to show you an example, which I hope will play again and again. You take a flat sheet, and you create this Miura-Ori, and you can approximate any curved object. You can essentially also mimic a sphere, or approximate a sphere. You can approximate a saddle. You can approximate a combination of a cylinder and a sphere, a cylinder and a saddle, or a sphere and a saddle. Okay? So these are calculations, these are computations, which we did, my students and I, and we showed that you can do this on a computer, and you can also do this experimentally. Now, you could have done this experimentally even without the computation, but it would have taken a very, very long time for you to essentially try all the different variations. And what this little bit shows you is that, in fact, you can do this first on a computer, which is very fast, and then you can realize this experimentally. Do people understand? Okay? All right. The problem is the following. The problem is that, in fact, these constraints are satisfied exactly only in the beginning and at the end, and in between you'll have to essentially stretch the sheet. That's one problem which you can deal with. Another problem is that if you have a very large number of variables, what are these variables? The variables are the locations of the vertices and the lengths of the edges. It's a very difficult computational problem to essentially solve. And there are ways to resolve that, and those ways of resolving that is to, instead of thinking about origami as a process by which you essentially prescribe all the folds and I give you the rules, I want to ask you for a minute to put on a hat associated with practicing origami. Where do you start folding? Anybody who's folded a complicated pattern, where in the sheet, once you're given the pattern, do you start folding? Anybody? In the center or the boundary, or where? Boundary. Why do you do it at the boundary? If you fold it at the center, all these constraints become very, very difficult to satisfy because I have to fold it one location, but some other fold interferes with it, and some other fold interferes with it. But if I do it at a boundary, it's very easy. Why? Because it's a boundary. On one side, you have no folds. Then you say, again, inspired by artists and inspired by people like all of us, say, instead of designing origami simultaneously, tell me where all the folds are together, can I essentially tell you how to change the fold pattern from a boundary? How do I essentially add one layer and then another layer and then a third layer in order for me to essentially drape my head? And the answer is, I can do that. I start with a square and then I figure out how to add a few squares around it which are folded, and then another layer of squares around it which are folded, and another layer of squares or rectangles, and I gradually can build it. Do people see that? Okay? And again, inspired by art. We were just observing. As I said, science is the ability to see what everybody sees and think what very few people have thought. So we did that. When you do that, you can essentially, again, I will not get into the details of it. I'll show you some examples of what you can do. So you can essentially create something which looks like an Elizabethan ruffle, something which will look very beautiful around a neck, or you can create something which looks like an aperture associated with a telescope, or crumpled sheets of paper, or all these remarkable shapes, and you can do this by just adding one layer at a time. Okay, I can do exactly the same thing. So I have a question. I can break now, or I can go for another 10 minutes associated with Kirigami relatively quickly. What do people think? So first of all, I should ask the host.
You have to close by 1:30, so you can go on and take questions.
Okay, so thank you. So what would people like? Can I tell you a little bit about Kirigami, or would you like to ask?
Yes. What's the next topic? What's the next one?
Kirigami.
You're interested about Kirigami, the next topic?
No, either Kirigami or I can stop now. Is everybody good with Kirigami? Will you ask me more questions? Okay. All right. So I told you about origami. Origami is folding. Kirigami is what? Cutting. So, but everybody thinks Kirigami is very different from origami. Why do you think so? Because it's associated with cuts. Origami is associated with folds. What I want to show you is if we think mathematically, there are enormous number of similarities. In origami, the slope, okay, so I told you, some of you have had calculus, some of you haven't. Maybe now I'll become a little clearer about, so this sheet has one slope. This sheet has a different slope. The slope is continuous over here, and boom, at that line, the slope is not defined. Because if I look at that curve, that edge over there, if I come ever so slightly on one direction, it has one slope. If I come on the other side, it's got another slope. So it's got a discontinuous slope. The function or the surface is continuous, but its slope is not defined at that location. With Kirigami, it's even worse. Even the function is not defined because I made a cut. And you would say, if you know calculus and you know fancy methods of calculus, all those break. Question. Can you hold on and then ask the question at the end? What is the important question? Yes, it has been used. Yes, by many people. NASA essentially uses origami-based techniques. What they do is they use very simple folds, like the Mura-ori. They're very simple periodic fold. What I'm saying is, and we've been talking, and other people who work in this area have been talking to people in engineering to ask, can I build more and more complicated folds? And I'll show you examples of that if you ask me at the end, or come and talk to me. Okay? All right. So in Kirigami, you have, even the function is not defined because you have a cut. Oh my God, when I come up from this side, the function looks like it has one value. When I come from that side, it has a cut. So the function has a different value. So it says, calculus doesn't work at all. But in fact, calculus, even if calculus doesn't work, a discrete approximation will work. And so what I want to show you is now, in the next 10 minutes or so, how do you do the same thing with Kirigami? So I first want to show you some experiments which were done by a set of scientists and engineers in Canada, okay, inspired by Islamic tilings. You see what's there. It's compact, so that means all the pieces are together. You pull on it, and boom, it expands. And it expands when the red and the white, or the green and the white pieces just rotate relative to each other. Do people see that? Okay, just by rotation. So again, you're preserving lengths, and you're preserving angles, except at a set of points. That's it. That's a simple example. So you can take a square, you can essentially have the right kind of cuts, and if you rotate them, they fully open out. Okay? And now I'll show you the connection. This is periodic, which means if I go, a certain distance, it looks exactly the same in this direction and in that direction, so it's periodic. It's contractible, which means it collapses. Fully compact, which means there are no spaces. When I open it, it opens out. It's rigid foldable. The whole thing happens in one motion. And it's also auxetic. It's got negative Poisson ratio. If I pull in one direction, it expands in the orthogonal direction. People see that? Okay? So it's like very similar properties to origami, except that it's associated with cuts. And so now, same question as in origami, given that all these hinges are 4 coordinated, so given the topology, how should we change the length of the edge? How should we change the orientation of the edge? How should we change the number of edges in order for us to do what? Instead of this boring pattern, I want to create a way to construct a circle from a square. Can you essentially construct a circle from a square? Take a square, you can't, right? Well, I'll show you, you can. Because what you would do is essentially open up gaps. And when you open up gaps, you can do all these beautiful things. Okay? So Greeks thought about this problem. A lot of people have thought about this problem. I want to ask, how can you do this? And the constraints are what? Just like in origami, if I come to a vertex, the sum of the angles is what now? 360 again. But these are now angles in the plane. And these lengths, A and B, must be the same. If this was C and D, they must be the same. If this was E and F, they must be the same, right? Because they're all in contact with each other. So you have some constraints. I can write those constraints. And here is a way. I told you that you thought you couldn't essentially construct a circle from a square, but here it is. This is the initial pattern we want to get here. Let me show you actually a physical example. Look at that. So mathematically, you solve this problem. You can convert a square to a circle. You can even do this with more and more accuracy by having smaller and smaller vertices. Okay? You can do this not just in 2 dimensions, you can do this in 2 dimensions, you can do this even in 3 dimensions. I will skip this slide because this asks a more technical mathematical problem. If I have a plane, I can ask how many ways are there of tiling the plane with a perfectly periodic pattern. You can do it with squares, you can do it with triangles, you can't do it with pentagons. You probably know this from experience. And there's a very beautiful set of ideas mathematically which shows that there are a set of patterns associated with symmetries which are called groups. And it's called the wallpaper group because it allows you to tile the entire wallpaper, and you can take every member of the wallpaper group and create a Kirigami pattern. And so again, I want to come back to this question that was asked before. Oh, here, science is inspired by art and then runs away. It sort of says all these other things that artists haven't yet thought about. So here is a way where now you're thinking about science, you think about art, the art led to science, the science is now leading back to art. Because I can think all these other patterns which artists haven't even yet thought about can be used. You can create quasi-crystalline patterns, you can do 3D origami, and my favorite example, which I want to show you now, is you can not only construct a square from a circle, but you can construct a square from a circle where instead of having gaps, let me show you, you keep opening it, and then it closes into a circle. And this is something that artists hadn't thought about. And now I have a friend who's an artist, and he saw this and he said, oh, I would love to start building this. So here's another example of where you started out with art, you went into science to understand what artists were thinking about, and then that science led to new ways of thinking about the art. So I want to again emphasize what I told you at the beginning, these boundaries are very, very artificial. And I encourage you to think that way. And here is a physical example that Levi Dute, a student who worked with me and he got his PhD, I hope this will play again and again. You keep opening it, it rotates and rotates and rotates, and then it closes and creates a circle on one side and a square on the other side. And you can do even crazier things. You can take a cone, you keep pulling it, and you think when you pull it, it stops, but you keep pulling it and it closes again, it becomes a long cylinder. And so somebody asked me about deploying solar sails. We think that this may be useful as a stent, because I can put it inside a vein, and if I put it inside a vein, I can put it in this form, and then I compact into that form, so I open it up. Okay? We weren't thinking about any of these things. We were thinking about it just from the point of view of curiosity. But that curiosity led to interesting things which perhaps somebody else who has a much more fertile mind in the context of translation and engineering can do that.
So this square to circle can't be done with the full square. As in, I mean, these are having gaps. Otherwise,
No, you can do it with the full square. You can do it with the full square. There are no gaps. It is possible. I can prove it to you, but we can talk about this afterwards. Yeah. As long as you have rigid rotations at the vertices, you can.
that question starts in italic.
So you're talking about it. So very good. So when I solve the problem in an optimization framework, then what I'm doing is essentially, I understand what you're saying. I'm doing it approximately using an algorithm, and so I can do it with any accuracy that you want. Of course, it's not exact. Yeah, absolutely. Yeah. But the gaps can be as small as you want them to be. That's why I said this is always an approximation. And I said right at the beginning that you can't also, for example, take a sheet and essentially tile it onto a surface of a sphere, but I can do it with arbitrary accuracy if you allow me to give you the smaller and smaller. And this is essentially what Nash and Gromov also showed in the context of convex integration, because you can go arbitrarily close even if you can't get there. The limit you never reach, but you can have a sequence, if that makes sense.
Sir, I had actually a doubt because
And I'm going
now,
to stop in a minute. Yeah.
yeah, I had a doubt actually
Yes.
regarding this. So I was wondering whether 3D printing can be done using origami and kirigami,
Yes.
because
Yes.
it's extremely effective light material which
Yes.
can survive in very volatile conditions, including
Yes.
in high density, low density conditions.
Yeah, the answer is yes, and I will show you some examples afterwards when you come, if you have a chance to talk to me. Okay, so I'm going to skip this because this is not but I'm going to use this as an example to finish. Instead of thinking about 3D printing, you can think about 4D printing, which is also including time, and I can ask questions, and I'll stop with this set of slides. So this is a pine cone. If you put a pine cone in water, how many of you have done this experiment? It will close. If I put a pine cone which is closed and take it out, it will open. And you can do this as many times as you want. Okay? And the reason you can do this is because at the base of the pine cone, you have cellulose fibrils, the same thing that pieces of paper are made of. And these cellulose fibrils, I'm going to go back, shrink and stretch. And so you can use this to take a piece of paper, and I was hoping to do this demonstration, but I won't. I'll ask you to try and do this at home. Take a piece of paper, take crayons and color one side. When you color one side, that side which is colored with crayons is non-wetting because the crayons are wax. On the other side, it absorbs water, and when it absorbs water, it will curl. And I did an experiment to show you something like what would happen. I just took a piece of paper and I put some water on it, and you see that the piece of paper with the water started to swell where there was water, but it's connected to the rest of the paper, and a consequence of that, it starts to wrinkle. So this is an arbitrary pattern. You can essentially do this cleverly. I invite you to try this at home. You can essentially create a flower which opens and closes repeatedly. And then, the response to your question, and I'll stop there, is my colleagues in engineering essentially took these ideas, which we helped a little bit from the point of view of mathematics to understand how to essentially take paper, grind it, mix it with clay, push it out through a nozzle. When you push it out through a nozzle, you can create a lattice pattern, and you can use that lattice pattern to essentially create stripes where you change the orientation of the stripes, you change the number of stripes, you change the location of the stripes, and then you wet it and you dry it, and what do you get? You get essentially the ability to mimic a flower. Okay? All right, so I will now stop here and close by telling you what I just showed you with two examples. One is taking that idea. My colleagues in engineering, Jennifer Lewis and her group, essentially showed that you can take a flat sheet, and let me show you the final example, and you want to take a flat sheet and convert it into a face. What you do is you discretize the flat sheet, so which means you, instead of having a flat sheet, you have a set of 3D printed fibers, which are no different from essentially strips of paper. And when you connect them together and you allow them to be wet or dry, which you will see on the right side over here, in a minute, you can essentially create an approximation to a face, because different parts are shrinking and stretching for different amounts. And so now you can see an approximation to a face. Do people see that? So you start with a flat sheet and you can approximate it and create something which looks like a face. Okay, so this is my last slide. So what have I shown you? I've shown you that we're playing with the configurational degrees of freedom, which means what? The location of the folds, the size of the folds, the orientation of the folds, and the number of folds. Or by doing the same thing with cuts, you can essentially take a flat sheet and do things which with continuous deformations you can't, but introducing these discontinuous deformations, you can get very, very highly accurate approximations to complex shapes, like all these that I've shown you over here. You can even approximate circles with squares and so on. I didn't really have a chance to tell you about something similar in printing, where instead of playing with these configurational degrees of freedom, folds or cuts, you can play with adding material. Adding material is essentially 4D printing or 3D printing. 4D corresponds to playing with time, and you can take flat sheets and convert them into faces. Okay? So, I've shown you this. There are all kinds of interesting questions mathematically associated with what you can and what you can't do. I didn't understand the question previously. You can't exactly convert a square to a circle, but you can approximate that. You can do this in 3 dimensions. And I will finish by telling you that all this is possible because I was very fortunate. I have been very fortunate to have worked with students slightly older than you over the last few years, in particular for this set of projects. Gary Choi, Levi Duke, Siheng Chen all got their PhDs with me and are off doing very different things. Lucy Liu is a graduate student who's continuing her PhD right now with me, and Caitlin Becker was a postdoc who helped us realize some of these things. Okay, happy to take more questions, and I want to thank you for your patience. Yeah.
So, I also built with origami. I also dealt with origami, and I had this question. Like, we had shown that model for art. So I remember Zhang Yu from Oxford. He had also used the water bomb base for making the heart stent model. Yeah. So how will your model be different from that? As in, I mean, from what I had read,
I don't know that work, so maybe we can talk offline. I don't know exactly which.
Zhang Yu. I mean, I have that.
Maybe, but I just don't remember specifics. What was the question though? He was using.
So you had shown that model in which, I mean, stretching it in one direction, it is just going to be going longer and longer as a cylinder, and while you could use it as a stent. So on once you.
That was the Kirigami model, not an origami model.
Yeah, sorry, the Kirigami model.
But I think what I understand is Zhang Yu were doing it with Kirigami or with origami.
An origami model.
That's different. So fundamentally different because we were opening up gaps and closing them, while over there he was playing with creases. If I understand, but maybe offline we can talk some more.
Sure.
I have a question over here.
Maybe questions from people who have not asked before, if that's okay.
When an insect emerges from the lava,
very
presumably
good.
that's origami,
Yes.
right? Are there examples of kirigami for insects?
I think yes, and I say I think because I have not looked at this work very carefully, but there is work which is associated with asking how crocodile scales form, but not on the body where they're very reproducible, but on the face where they're very irreproducible. And there is a suggestion from a group in Geneva that is of the opinion, by basically looking at embryogenesis, that these patterns of scales and form by essentially having the inside, the dermis, grow relative to the epidermis, and so the epidermis is put into tension and starts to crack and fracture. But when it cracks and fractures, it doesn't completely rip, it remains articulated. So it may be that that's an example of where kirigami is used. And why is the face a place where you want relatively irreproducible patterns? Is for recognition. A lot of animals will recognize other animals not by looking at the body, but by looking at the face. In fact, even insects can do that. Wasps can recognize other wasps. So if you want irreproducibility, you don't want something which is very hard-coded genetically, and you want to use some ideas from maybe these kinds of simple examples. But I can offline tell you a little more about that. I don't remember the exact reference. Others would not ask questions.
Sir, this is a very hypothetical idea, but can this folding and cutting be altered to change this DNA of species and carry more information?
I can't hear you. Can change if people
Can change the DNA of species, like altering the DNA and carrying more information in the DNA?
Yeah, I was thinking on I'm thinking about large scale phenomena. So I'm not thinking about DNA. DNA is a double, if I understand, you're thinking about DNA as a double stranded helix. Is that what you're thinking about?
No, DNA in a, just say, in a blood, DNA. So we can alter the DNA.
DNA is a molecule, unless I misunderstood. So what about the DNA?
So can we alter the DNA in such shapes that it can carry more information?
Yeah, so there are people who work with synthetic versions. There's a whole field called DNA origami, which was started by a chemist called Ned Seaman. And what they do is to essentially use the ability of DNA to replicate very easily and very reproducibly, but then change the nature of the junctions where DNA can combine with other DNA, associated with something called holiday junctions. I can tell you about it offline. So people have essentially used this synthetically. They have not used this in any biological context.
Okay.
Sir, so you talked about how
Can you speak up?
You talked about how origami and kirigami have been used in like a few objects, something like a sailboat where the sail used up kirigami. So my question was, can origami and kirigami be involved in more daily life objects, tools and machines to make them efficient? Or
Can what?
can origami and kirigami be used in more daily life objects, tools and machines to make them more efficient?
I think there's a whole field of DNA and of origami and kirigami based engineering. For example, I have a colleague who showed me a kayak, a boat, not just a paper boat, but a boat in which you can sit and then row. And this is, I think, a company called Oru Kayak or something of that sort. So you can essentially fold the kayak, put it in a backpack, and then you can go to your local river or lake and then open it up, and then it will essentially unfold into, So people are just recently starting to think about using these to create functional, everyday objects like boats, like flexible antennae for electromagnetic wave propagation, which is sensitive to different wavelengths depending on the nature of the origami. Similarly with kirigami. What was limiting us so far was that the designs were primarily simple periodic designs, the ones like the Mura Ori that I showed you, or these ancient Islamic tiling patterns. But if I want to get more and more sophisticated function, then I also need to have more and more sophisticated shape. But in order to get more and more sophisticated shape, there are two ways. One is trial and error, and the other is what I tried to show you over here, which is to be systematic about what the constraints are, what is the shape that you want to get to, because you as a designer, as an engineer, tell me where I want to get to, and use algorithms like the ones that I showed you. Okay, and so now I think there's likely to be a convergence of these powerful inspirations coming from art, combined with the algorithms which are based on some very simple mathematical principles, and the power to essentially calculate. I didn't tell you about a third leg of all this, and the third leg is the ability to calculate computationally quickly. Okay, so that's something that I just decided I couldn't spend time on. So, you have artistic inspiration, you have engineering relevance, and then you have the ability mathematically and computationally to put all these two things together. Does that answer your question?
So I had a doubt when you were talking about how a cone could be opened into and contracted into a cylinder, and how that could be used.
Also a cone. It's not a cylinder. You can never go from a cone to a perfect cylinder. It's a cone, but with a different angle. But yes, yeah.
So even though it does help with transportation, wouldn't that end up like in the context of solar sails? Wouldn't that end up causing a lot of more failure points?
As soon as you have hinges and creases, the question that you raise associated with failure points is a very important one. So there's no question. I deliberately did not focus on the materials aspects and the engineering aspects. I focused on the mathematical aspects because I thought that those would be the places to start. First, to show that it's feasible. If it's not even feasible, then the question of building something is out of the question. Once you've shown that it's feasible, then the next level question is, how do you engineer it? Create 1 or 2 models, and the next level question after that is, how do you scale it up so that I don't build 10 of them, I build 10 million so that everybody can have it. So those are questions which we and others are thinking about, but it's still early.
Thank you.
So,
Someone who hasn't asked the question.
sir, could you please provide some examples of kirigami in nature, for example, in leaves and insects?
Yeah, that was the question that was asked before, and I'm not sure I know an example for sure, but one possibility is the morphogenesis of scales in crocodiles and other reptiles. But I'm not sure. I don't have a very good example that I can think of immediately of kirigami in nature.
Sir, so so you mentioned about
sorry.
how...
Yeah, thank you.
Yes, sir. So you mentioned how kirigami and origami, the mathematical aspects of it could be applied into other applications in real life. And you mentioned that there is a field of engineering that works in it. So obviously there's a lot of data to be handled in that field and a lot of analysis and modeling to be done of how the aspects of kirigami and origami can be used to, for example, make engines more, or I mean, any kind of machines more efficient. So how, could you touch up a bit upon how the mathematical modeling and analysis, or like topological and geometric analysis works in this kind of a scenario?
Let me see, I understand your question. So you're asking how do these ideas end up being used? And is that your question?
How mathematically you could analyze basically how the system would work through such a model.
Well, I showed you examples of if I want a particular shape, how do I get there? Yeah. What I didn't show you is if you have that particular shape, how does it enable some function associated with an antenna, a solar panel, maybe a shade, maybe a kayak, maybe something else. I didn't because we don't work in the areas which are directly connected to the engineering applications, but we talk to our friends and colleagues over there. Without the mathematics, this last example that I showed you of how to create an artificial version of a flower or a face, it would have been impossible. Without the mathematical underlying basis for figuring out how to solve this inverse problem, how do I print these thin filaments of mixture of clay and wood, where do I put them, when do I put them, how many do I put? If you tried it purely from an experimental, empirical point of view, you would have to try many times, and you would probably never get to the answer because the number of combinations is just very, very large. So the role of mathematics and computation, I should emphasize, which go hand in hand, is to essentially reduce, by introducing constraints as to what is physically possible, what is geometrically possible, is to reduce the space of possibilities to a small enough number so that you can search that space much more efficiently and then talk to the engineering colleagues and then say, here's what you should try. If you didn't, you're just working with trial and error, you would be remarkably successful at simple patterns, but as the patterns start to become more and more complicated, because the number of possibilities starts to essentially become very, very large, combinatorially very large, it becomes impossible to search. So artists are successful precisely because what they do is not very reproducible. Now, that's why Picasso is Picasso, or M.F. Hussein is M.F. Hussein, right? Because they do things and nobody else can do what they do. And the scientist essentially is exactly the opposite, or the engineer is exactly the opposite. Say, I want to do this so that anybody can pick this up and do it. So if you see what I'm saying?
Yeah. This question specifically popped into my mind because you mentioned the irregularities and non-recurrence of patterns in the development of... So basically, a single pattern would not repeat over a sequence, or like it would not repeat in case of certain models.
I didn't say that at all. I said that you can have algorithms which will give you the pattern that you want. So I'm not sure what you mean by that.
I meant that basically there would be some level of increase in complexity of models of recurring simple patterns, if I understood you correctly.
Maybe we should talk separately.
Yes, sure.
Okay.
Yes, sir.
Hello, you said that you see more into the mathematical applications of this, but I had a question related to what are your views on the biomedical engineering aspects. So will this kirigami and origami can also be used making like stents or the other to replace something in our human body instead of like machineries which are used? Would you think in future they could be replaced? with this?
Possibly. I mean, people have used origami-based stents already. Based on Kirigami, I don't know of anybody, but that's also because until the work that I described, people weren't thinking of using these Kirigami-based ideas. So maybe in the future they would be. And maybe this is a way also for me to address this question of, one shouldn't always think, in my opinion, of what is this good for, what is the application. One can start by thinking about it because you have an interesting question, you're curious about the world as it is, and then try to understand it. Going to the next step and asking, oh, is this useful for something? Perhaps, yes. I don't know. That's not something that we've focused on so far. Yeah.
So there was a technique called growing in the previous slide. Can you emphasize on it, sir?
I couldn't hear you.
Yes, sir. So there was a technique called growing, I think, in the previous slide.
Yeah.
Can you emphasize a bit more about it, sir?
Growing is what happens to you and me. We started out as a single cell, and then in 9 months, the cells divided, took nutrients from your mother, and created a very complex sentient organism, which in a few years is able to ask questions about its own being. Okay? In the context of the physical aspects of growing, it's equivalent to adding material, or having material which swells or shrinks. So paper, when it's wet, starts to swell. When it dries, it starts to shrink. That's true for wood. Okay? If you have you had a gulab jamun? Okay, so gulab jamun, have you ever seen how it's made? Okay, so when it's made, next time take a look, but let me tell you. So gulab jamun is made by taking some wheat, some milk, protein, and some fat, and then making a round ball, and you put it inside boiling oil, and when you put it in boiling oil, all the water, almost all the water is lost. And then what do? You dip it inside sugar syrup. And when you dip it inside sugar syrup, it swells. So it's kind of growing. It's not real growth because you're not adding more gulab jamun, you're adding the sugar syrup. And so when it grows, if you look at it carefully, you will see that the surface wrinkles. And then those wrinkles become larger and larger and larger, and eventually they disappear. So that's growth, but it's growth because you're adding material from the outside. So now the question becomes, you said, what do we think about in the context of growth? We ask questions about how, if the gulab jamun was not growing uniformly everywhere, instead of remaining a sphere, can I create a cylinder? Instead of creating a cylinder, can I create a face and whatnot? That means different parts have to absorb water differently. And I invite you, I'm sorry I didn't have a chance to do this, take a piece of paper, draw complicated patterns or even simple patterns with a piece of crayon, wet the paper, different parts will swell differently because the parts which are waxed with the crayons will not, the other parts which are not waxed will. That's a simple version of growth. And so one can ask exactly the same kind of question that we asked with Kirigami and Origami with growth, inspired by what happens with the body. Does that help?